So this is continuation of our last lecture on electric potential and capacitance, where we discussed the electrostatic potential energy, what is electric potential, potential due to dipole, relation between electric field and potential, right? Okay. So let's discuss one more topic here, which is equipotential surface. Equipotential surface. So as the name suggests, right, equipotential surfaces are surfaces of equal potential or constant potential, right? So around a system of charge, if we have any surrounding where we have equal potential all around, the locus of that surrounding is nothing but a equipotential surface, right? Let me give an example. Okay, so let's say this is a point charge plus q, right? This is a point charge plus q. We discussed the potential due to this point charge any at any point is nothing but kq by r, right? Kq by r. So k is already a constant, right? Coulomb's constant. Q is a charge, it is also constant. What is variable? R. So if I need potential as constant, I need R also as constant. Then only my V will be constant, right? So at a constant R, if I see at a constant R, at a constant radius, if I take all the constant R and draw a particular surface, the surface will look like a circle, right? And again, this R can be some different value as well. So if I pick one particular circle, all points on that one particular circle will have common potential, right? So I can say that equipotential surface for a point charge are nothing but concentric circles, right? These are nothing but concentric circles, right? Clear? Right. So for a point charge, we discussed that equipotential surface will be concentric circles, right? If we talk about 3D, so equipotential surface is nothing but concentric spherical surfaces, right? Okay. Now let's simplify this diagram again. Let's take only one circle. So this is my point charge plus q, right? And this is a equipotential surface around this, right? Now if I need to find electric field over any point, at any point on the circle, right? Let's say this is a point A and again at a distance r. So what is the direction of electric field here? This will be in this direction, which is nothing but kq by r square. At any point, if you see, the electric field is nothing but perpendicularly, radially outwards, right? So can I say that electric field is always perpendicular to these equipotential surface, right? Now let's understand analytically why, right? So again, let's say this is a charge, this is a equipotential surface, right? And equipotential surface means at every point on this surface I have a constant potential, constant electric potential. And if I need to move a charge from any point to, let's say from A to B, there should not be any work done in this particular case because it is a point of constant potential, right? And let's say if electric field is not perpendicular but it has some component on this particular surface, right? Let's see if it is not perpendicular, it may have some component on the surface. And if electric field has some component on surface, you know by expression E equal to minus dv by dr or v equal to integration of edr, there will be a potential on the surface, right? There needs to be work done to move any charge on the surface, which is violating the definition of electropotential surface, right? And hence we can conclude that direction of electric field, direction of electric field is perpendicular to equipotential surface, right? Let's draw one more equipotential surface, right? Let's draw one more equipotential surface. So if we talked about uniform electric field. What is a uniform electric field, right? So this is a section of uniform electric field, right? where I'm indicating the magnitude. This is a uniform electric field, right? The field is increasing in this particular direction, right? Okay. Now, if I need to draw equipotential surface for these field lines, so what will be equipotential surface will look like? It will look like these square sheets, right? Won't it look like these square sheets? We just discussed the electric field will perpendicular to the equipotential surface. So these square planar sheets, the will be the equipotential surface for this uniform electric field, right? Okay, you can understand by definition, right? Now let's say we have a system of dipole, right? We talked about dipole. So let's say we have plus q, then we have minus q, things like that, right? Okay. Now again, a dipole, if I take standalone charges, this will have a concentric cell type of potential surface, right? Again, this will also have same, right? Be independent of the charge magnitude, the equipotential surface will look similar to this, right? But we know that equatorial position of dipole we have zero potential, right? So there won't be component around the equatorial position, right? So this is like how equipotential surface for a dipole looks like, right? So in similar way, you can draw equipotential surface for different bodies, right? So equipotential surface are nothing but surfaces of constant potential, right? At any point, if you take, the potential will be constant, right? Right. So we discussed about relation between potential and electric field intensity, right? Potential is a scalar quantity. Electric field intensity is a vector quantity, right? So we discuss E is nothing but dV by dr. Or before that, we discussed V is nothing but negative of integration of dot product of E and position, right? Let's say this is the system. My electric field is from A to B. Uniform electric field exists, right? And electric field is given by, let's say, exi cap plus ey cap plus ez k cap, right? So this is electric field along all three directions, right? We discuss in the vectors, right? So ex is the component along x, ey is the component along y axis, ez is the component along z axis, right? What about dr? Dr is nothing but position vector, right? So dr will be nothing but dx I cap, dx in the x, dy j cap, and dz k cap, right? And if I do a dot product, so how this v will look like? V will look like nothing but v will look like minus of ex dx, right, plus ey dy plus ez dz, right? V will look like this, right? If I take all three components, right? But now if I need to find what is ex or what is ey or what is ez, how I can find that? Ex is nothing but minus of dou by dou x, right? Ey is nothing but minus of dou v by dou y, and ez is nothing but minus dou v by dou z. So what is difference between dou v by dou x and dv by dx? So this is what is partial differentiation, right? So partial differentiation, when we do partial differentiation, we come across a scenario when we have multiple variables, right? So generally we differentiate with respect to x, we assume that only x is the variable. But what if we have a function of x and y and we need to differentiate with respect to x? Then we go for this partial differentiation and we assume y as constant and then we differentiate with respect. Let me give an example, very quick example. Let's say if function y equal to xy square, right? And I need to do a dou y by dou x. So I'll assume y is constant, I'll take it out, and then again dou x by dou x is 1, so y square is the answer. So this is nothing but partial differentiation, right? Okay. So this is how we can calculate the electric field in x direction, y direction, and z direction if we have the potential expression given, right? Now let's solve some problems on electric potential, right? So the problem looks like, let's say there are four corners of a square, right? These are four corners of a square of side A, right? Side is A. At four corners, the charges which are placed looks like this. So at opposite corners we have plus q, this is also plus q, then we have minus q, and then minus q, right? And problem is we need to find the work done to bring this system of charge together, right? We need to find the work done to bring this system of charge together, right? So basically we need to find the potential energy of this particular system, right? Okay. So potential energy, we know that if we have two charges q and q, let's say q1 and q2, separated by a distance d, the potential energy will be nothing but k q1 q2 by d, right? And since potential energy is a scalar quantity, I am not worried about triangle law, direction, and things like that, right? So we need to find a pair of two over here, and then we need to find the potential energy, right, of net system, right? Okay. So let's say the points are mapped as this is point A, B, C, and D. So A and C has plus Q charge, and B and D has minus Q charge, right? So how many total combinations are there for these four charges? Can we calculate this, right? See, the combination will look like this. I'll tell you. So A to B we have one combination. AB is one combination. First of all four sides are one combination. Then BC is one combination. CD is a combination. DA is the combination. And then diagonally also we have a combination. So other combinations are AC and BD, right? So there are total six combination, right? We can also find it by 4C2. 4C2 is nothing but 4 into 3 by 2. So this is nothing but total six possible combinations we have. So six possible combinations of charges we have, right? So let's calculate one by one. Let's calculate one by one, right? So potential energy because of this system VAB. VAB will be what? The distance is A. So KQ minus Q by A, which is nothing but minus KQ square by A. This is VAB. What about VBC? VBC is nothing but, again, VBC has similar set of charges. So it is again same, and it is also minus KQ square by, which is also same as VCD and also same as VDA. So all four combinations which are along the sides of square gives me the same potential, right? Same potential energy. What about diagonal combinations? To find the diagonal combination, we need to find the distance between these two charges along diagonal, right? So this distance is nothing but root 2a, right? Because this is a, this is hypotenuse of this triangle, so this is root 2a, right? So along AC, what is VAC? VAC is nothing but K plus Q by root 2a, which is KQ square by root 2a. Again VBD is again K minus Q by again root 2a, same value of diagonal. So this is also KQ square by root 2a, right? So we have total six combinations. We will find the net potential, right? So net potential, if I find, let me write it properly. So net potential is nothing but VAB plus VBC plus VCD plus VDA plus VAC plus VBD, right? So these four have same value, right? I can just place it like this: minus 4 of KQ square by, and these two we have just calculated. This is nothing but KQ square by root 2a plus KQ square by root 2a. If you solve this, you will get KQ square by a and then minus 4 and then plus root 2. So this is nothing. This is what I have written as V, but this is actually energy. This is nothing but U. So this much amount of this joule of work is to be done to bring all this system of charges together on side of this square type system, right? Okay, right. So next topic is electrostatics of conductor, right? So we already studied when we were talking about electric field, electric force, that inside a conductor, let's say there is a conductor. Inside a conductor, there are no excess charges, right? Inside a conductor, there are no excess charges. There are neutral amount of charges, right? So even if you try doing by Gaussian surface or something like that, you will come to a conclusion that electric field inside a conductor is always zero, and hence electric flux is always zero, right? So this is first point when we talk about electrostatics is conductor, right? So electric field inside a conductor is always zero, right? Okay. Now, if I talk about field lines, right? If I talk about field lines, So electric field lines will always be perpendicular on the surface of conductor, right? Electric field lines will always be perpendicular to the surface of conductor, right? Before dealing with electric field lines, we need to understand and identify that electric potential inside a conductor or at the surface has the same value throughout, right? We discussed the relation between electric field and potential, right? E is nothing but minus dv by dx, and we say that electric field inside a conductor is zero. So potential inside a conductor, we have constant potential, and which is also same as potential on the surface, right? And hence this is kind of equipotential surface, right? An electric field will always be perpendicular to the surface of conductor, right? Whatever be the charge, electric field, it won't be inside, but yeah, perpendicular to the surface, right? So let's say if this is a positive charge conductor, electric field lines will look like this, and there won't be any lines inside the conductor, because inside the conductor electric field is always zero, right? Okay, right. So next topic is electric field at surface of charge conductor, right? Surface of charge conductor. So very quickly we'll find what is the electric field at surface of a charge conductor. So this is a charge conductor. It has charges on the external periphery, right? So if I need to find electric field on its surface or its nearby points, we can apply Gauss law, right? What Gauss law is? Gauss law is nothing but it says the surface integral of electric field is nothing but it is given by charge enclosed by epsilon naught, right? Okay. So this is a surface delta S I have picked from here, and I have indicated the direction of electric field as normal to the surface, which we just discussed, right? Okay. So now if I apply this Gauss law, this E and delta S will be what? Charge enclosed by epsilon naught, right? Sigma is the surface charge density, right? So if I need to find the charge will be nothing but sigma into area delta S, right? So can I put it like this? This net charge, this is Q in. So in E del S is nothing but sigma del S by epsilon naught. Del S will cancel. So electric field will be given by sigma by epsilon naught, right? So based on magnitude of sigma, I can say the field is outwards or inwards. Positive sigma is outwards, negative sigma is inwards, right? And this is how we know the electric field direction is away from positive and towards the negative, right? And next term is, there is a term called electrostatic shielding, right? Electrostatic shielding. Electrostatic shielding. We know the inside the conductor electric field is always zero, right? So if there is a conductor, right? If there is a conductor which has a cavity inside, this is a conductor and this is the cavity. This middle surface is the cavity. It has a hole or something like that, right? Okay. So how this conductor will be useful? So we know inside all the points on this conductor, electric field is zero, right? It is also clear from the Gauss law, right? And even if any external charge, charge impulse or any surge comes on this conductor, whatever amount of charge which will come, it will come on the external periphery, right? It will come on the external periphery. So if I have some appliance, right, which is very sensitive to these charges, external charges and things like that, which is very responsive to that, I can actually place that particular appliance on this cavity, and whatever be the situation externally, my appliance will not be affected because it is shielded from all the external world, right? Because we know electric field inside this cavity will be always zero. We have discussed before as well. So this phenomena is called electrostatic shielding, right? Right. So next topic is dielectrics, right? So we discussed that based on conductivity, we have two types of classification of materials. One is conductor and one is insulator, right? Conductors and insulator. But there is one more category which is of dielectric, right? So in certain situation, it will be insulators. Certain situation, it may get behavior of conductor as well, right? So how a dielectric is different from a conductor, right? So dielectric is basically an insulator, right? But let's say we have a conductor, right? Let's say we have a conductor. This is a conductor, right? And if this is placed in external electric field E, this is the external uniform electric field E. What this electric field will do? This will bring negative charge of the conductor at one periphery and positive charge at one periphery, right? And there is an internal electric field also developed inside this conductor, and we know that this splitting of charges will stop when E will be equal to E in, and net electric field, which is E minus E in inside conductor, will be what? Zero, right? This is a case of conductor, right? But if I talk about dielectric, right? Dielectric, what happens is this separation of charges would obviously happen, but they are not strong enough as in case of conductor, right? They are not strong enough. So this E in which is developed here, E in is less than E, or I can say E in is not equal to E, and hence minus E in is not equal to 0, and hence there is a net electric field inside this particular dielectric, right? And if there is a residual electric field existing there, it results into the polarization of that dielectric. It develops a polarity. Before it might be polar or non-polar, but now it develops a polarity when it was placed in a external electric field, right? Let's understand in terms of chemistry, right? Let's understand in terms of chemistry. So let's say, let's take example of two molecules, H2 molecules, right? H2 molecules. So this is a non-polar molecule, right? This is a non-polar molecule. Why? Because these two molecules are symmetric. These two atoms are symmetric to each other, and they have similar kind of polarity, right? A similar kind of attracting power of shared electron. So there is a shared electron here. So whatever capability of this H has, this H also has same capability, and hence this is a non-polar molecule, right? This is a non-polar molecule, right? But if I talk about a polar molecule, right? Polar, let's say water is a polar molecule, right? So this is oxygen, and then let's say this is oxygen, then this is hydrogen, and this is again hydrogen, right? So there also you see this, there is a shared pair of electron, right? Now this oxygen, we know that it is more electronegative, right? This is more electronegative. So this has tendency to keep this shared pair of electrons towards itself, right? So this has a significant polarity, right? You see this is kind of two dipoles existing here. Directions will be in from negative to positive, it is. So yeah, this is direction, right? So this is a polar molecule and this is a non-polar molecule. And how these two are different? So here, if you see the center, the negative charge and positive charge center, they will be coinciding to each other, right? They'll be overlapping to each other. But here, if you see, the centers are different. The centers of negative charge is lying away, the center of positive charge is away, and hence this is a non-polar molecule, right? But what happens in case of non-polar molecules? We discuss the centers will be coinciding with each other, right? Positive and negative charge will be coinciding each other. In case of polar molecules, the centers will be different, right? Something roughly, if I make something like this, right? So we have distinct separated centers, right? This is case of polar molecules, right? And this is case of non-polar molecules. But if this non-polar molecule also placed in an external electric field, as we discuss, it may get this separation of centers and it may get some polarity, right? And this polarity, development of polarity, this phenomena is called polarization, right? This phenomena is called polarization, right? Let me write this term. The phenomena is called as polarization, right? The phenomena is called polarization, right? So we just discussed that if any external field is applied to this particular non-polar molecule, the centers of charge will be separated and it will turn like this. And now it has a dipole moment, right? Because there is a separation of charge, and whenever there is a separation of charge, there is a dipole moment, and this dipole moment will make this molecule polar now, right? And the amount of polarity, how this amount of polarity varies with this electric field. So we have expression for that. So this amount of polarization is directly proportional to electric field, right? And if I remove this proportionality, this is given by xi e into e, right? So this xi e term, it is called electric susceptibility, right? This is electric susceptibility, susceptibility, right? And this is the constant characteristic for a dipole, right? So this polarization, amount of polarization is proportional to electric field, external electric field applied, and on removing constant we'll get a constant called electric susceptibility, which is characteristics of a dielectric, right? So we just discussed on how an electric external electric field can polarize a molecule, can develop a dipole moment in a molecule, right? So from next lecture onwards, we'll be talking more into the separation of charges. We'll be talking more into a device which has a separation of charges, which is called capacitor, and it has a property called capacitance, right? So for till then, thanks.